For nearly a decade, the disappearance of Malaysia Airlines flight MH370 has challenged investigators, engineers, and analysts around the world. Satellite communication data provided important clues, specifically burst timing offset, or BTO, and burst frequency offset, or BFO. But traditionally, these signals have been treated as isolated data points, used only to define large geographic search areas. What you're about to see approaches the problem from a different perspective. Instead of using BTO and BFO simply as positional constraints, this system treats them as a dynamic measurement framework, one capable of reconstructing how the aircraft was actually moving. Not just where it might have been, but how it got there. This method, signal-derived motion reconstruction, combines signal physics, Doppler behavior, and aircraft maneuver geometry to isolate the flight path that satisfies all constraints simultaneously. Rather than starting with assumptions about geography, we begin with the signals themselves. And as you'll see, the aircraft's motion is not drawn, it emerges. What you're seeing here is the full Doppler shift, which can span large values, positive or negative, depending on how the aircraft is moving relative to the satellite. But the system we're using doesn't rely on the full range of that signal. Instead, it applies a controlled window, a set of internal guardrails that focuses only on the portion of the Doppler shift that produces stable, continuous motion. So even though the raw signal might show large frequency changes, the directional system operates within a much smaller band. From turn to signal constraint. One turn, physical motion, what the aircraft is doing. The aircraft does not change direction instantly. It moves through a continuous curved transition with a measurable midpoint. That midpoint is not just geometry, it is where motion, timing, and signal begin to align. The turn is smooth, continuous, and constrained. No jumps, no discontinuities. What you're looking at here is not a flight path yet. It's the validation system behind the flight path. This image shows how an aircraft's position is constrained and verified using two independent satellite signals. BTO, burst timing offset, gives us distance. BFO, burst frequency offset, gives us direction and motion. Start with the foundation. The rings. These circular rings you see, those are BTO distance constraints. Think of them like guardrails. Each ring represents how far the aircraft is from the satellite. The aircraft must stay on one of these rings at any given time. There's no guessing here. This is physics-based timing. So right away, we've locked the aircraft into a fixed distance zone. Add motion. The Doppler band. Wrapped around the outside, you see this color band. Blue, moving toward the satellite. Red, moving away from the satellite. This is your Doppler shift, BFO. This tells us not just where the plane is, but how it's moving relative to the satellite. What you're looking at here is the aircraft's heading mapped directly against the Doppler signal. This is where motion becomes measurable. At takeoff from WMKK, the aircraft is pointed at 320 degrees. That direction isn't just a heading on a compass, it's also a direction relative to the satellite. Now here's the key. The BFO value, -114. Hertz tells us the aircraft is moving away from the satellite. So what this image is doing, it's locking those two ideas together. The compass heading, 270 degrees. And the Doppler shift, -140 Hertz,